What's going on, guys? Today we're going to go ahead and look at 6.2, which is the volumes. Okay, the best way to always look at this is through an example, but to start off, we're going to talk about what is a volume. So a volume is basically an area times the height. In the case for us, the volume is going to equal the area times the thickness. Okay, and when we're looking at it in 6.2, we're going to be looking at it through very small slices to get the most accurate area, and we use that through an integral. So usually our thickness is either going to be in terms of dx or dy, depending on how we look at it. So let's go ahead and see this through an example. Okay. So consider the function y equals 9 minus x squared. The area between the function and the x-axis is the base of a solid. Find the volume if the cross sections perpendicular to the x-axis are A squares and B equilateral triangles. Okay, so what does this mean? So what it means is we're going to consider the function of y equals 9 minus x squared, which you should know that it's a parabola, especially an upside down parabola. And it's between the parabola and the x-axis. And in that base, you have solids that are going to come up through it. You have to find the volume of this cross section that is perpendicular to the x-axis. So let's go ahead and draw that out. So we're going to draw it out. We know that it's an upside down parabola. But how can we go ahead and get an accurate drawing? Well, we can grab our function, which was y equals 9 minus x squared. If we set y equal to 0, we can find our x-intercepts. So we'll grab 9 minus x squared. What we'll do is bring x to the other side, which gives us x squared equals 9. Take the square root. So x equals plus and minus 3. So we know that at plus and minus 3, this parabola is going to intersect our x-axis. Now let's see where it intersects our y-axis. If we set our x to be equal to 0, what do we get? Well, we just get y to equal to 9. So our parabola is going to look something like this. Okay, and so we go back to the example. The area between the function and the x-axis. So the area that we're looking for is this area here, where these two meet. So let's go ahead and erase this. So it's telling us that we have a solid, a base of a solid, that is cut into minute pieces that is perpendicular to the x-axis. Meaning And in this case, in part A, they're squares. So this one, you kind of have to draw it out as kind of like a 3D figure. So we're going to draw it a little different. So if we tilt our coordinate system, and here's 9, we know it looks something like this. So that's the base. But they're telling us that at some point, we don't know what point along this line, there's a solid with the base perpendicular to the x-axis, and it's a square. So to find the volume of this shape, because we're going to have different minute little cuts here to create some type of 3D shape, and each one we have to go ahead and take the area of it and the thickness of it and add them all up. And the way we can do that is through an integral. That's what an integral does. It dissects things so small and adds them all up for you. So we have the volume, an integral between a to b, as we're looking at it through some type of space between the x-axis, which is the area, times thickness. So let's go ahead and draw out our cross-section, which in this case is going to be a square. So this is our cross-section. And as you can see, our thickness is going to be here. So with our thickness being here, we don't know what this thickness is. But we know that our thickness is usually going to be, since it's along the x-axis, it's going to be with respect to x. So our thickness in this case is going to be dx. Now the area of a square is side squared. Okay, so our volume between a to b is side squared dx. The issue we're having though is we have two different variables. We need to make sure that s is in terms of x, because that's what we're looking at it through. But according to the graph, we know that our base, or this s here, is equal to our function, or whatever our function or y value for our function would be. Here, this is going to be a y value. If we were to draw another one here, it's going to be equal to the y value here. So we know that s is equal to y. And if we go back to our equation, we know that y equals to 9 minus x squared. So we can use this to go ahead and substitute it for y, and we can use this to manipulate it to go ahead and substitute it for s. So if we know that s equals y, we know that s equals 9 minus x squared, right? So what we're going to do is, if we know that that's true, then we go ahead and just plug that into our formula. Volume from between a to b of s is going to be 9 minus x squared dx. We substituted our s into s squared, which gives us 9 minus x squared. Now we got to go ahead and find where we're looking at through our a and b. So our volume, if we look at our graph, we know that this was -3. We know that this is 3. So we're looking at it from here to here. We're always looking at it, or in this case, we're looking at it through the x-axis, or dx. So our a and b for this problem is -3 to 3. The a value is usually the smaller number, and the b value is usually the larger number. So we're looking at through 9 minus x squared dx. Now, if we plug this into our formula, or try to plug it into the calculator, if you have a integration button. If not, we're going to need to take the antiderivative of this. Now, it's not so hard to take the antiderivative of this, but it's just time consuming. So I would say if you have a calculator, get a calculator that has an integration button. If not, you can do the problem. We can figure it out. So the volume of -3 to 3. So we have 9x squared. So that's 9 minus x squared. 9 minus x squared. That's going to give us 81. We're going to go ahead and distribute this one, distribute that one. Going to give us 81 minus 9x squared minus 9x squared. So it's going to be 18x squared plus x to the fourth. So our volume with the integral between -3 to 3 is going to be 81 minus 18x squared plus x to the fourth dx. So then, now we have to take the antiderivative of that. So our volume, the antiderivative of 81 is 81x minus 18x cubed over 3 plus x to the fifth over 5. And we're looking at it between -3 and 3. And now we can go ahead and use our f of b minus f of a. So we're going to go ahead and plug this in. So we have our f of b, which is going to be 81 times 3 minus 18 over 3 cubed plus 3 to the fifth over 5. That's our f of b. Now we have our minus f of a, which is just plugging in -3 into that. So we're going to have 81 -3 minus 18 over 3 -3 cubed plus -3 to the fifth power over 5, and that is our f of a. And we plug this into the calculator, we're going to get that our final volume is going to equal 1,296 over 5. So that is the volume of this 3D shape that they describe for us, cutting it into minute squares. So not too difficult. And let's go ahead and try to do part B now. So in part B, it's the same example, but they told us that our graph, which was from -3 to 3, the height of 9, is going to be cut into perpendicular cross sections, but this time they're going to be equilateral triangles. So let's go ahead and pull our cross section out. So this is what our cross section looks like. So we know that our thickness is going to be here. So this, we don't know what the actual length of that or that thickness is, but we know that it's with respect to x. So we know that it's going to be dx. And we know the area for a triangle is equal to 1/2 base times height. So, easy enough, we're going to go ahead and say the volume between the integral, which is going to be the same range that we looked at before, which was -3 to 3, and our area, which is 1/2 base times height dx. The problem we're having now is we have a b and an h. We have two different variables that need to be x's. So what we're going to do is we're going to look at our triangle through a different lens. So we know when it's an equilateral triangle, we know that this side's b, this side's b, and this side's b. So we got to go ahead and find a way that we can correlate b and h and make them somehow plug into each other, or find a formula where we can plug in one for the other. So if we know that this is b, we know that this is b over 2. So now we can either use, we know that if it's an equilateral triangle, these angles must be 60 degrees. So if this is 60 degrees, we can go ahead and use SOHCAHTOA. So sine of 60 degrees is equal to opposite over hypotenuse, which is this triangle that we're looking at. So we should know what sine of 60 degrees is. That is square root of 3 over 2 equals h over b. So we solve this for h. We're going to multiply by b. So our h is equal to square root of 3 over 2b. So we can use this to plug it in here. So our volume is equal to, from -3 to 3, integral from -3 to 3, 1/2 base, then we have times square root of 3 over 2b dx. We can simplify this. Our volume is equal to, from -3 to 3, square root of 3 over 4b squared with respect to x. Okay, so we got one variable out, or h out. But the issue now that we have is we have b. And we know that the base, which is here, is dictated by our y. So we know that b is equal to y. As we go here, our base has a different y value, and here, and here. So if we know what y equals, which y is equal to whatever the formula for that function is, which was 9 minus x squared, we can go ahead and solve it for whatever. We can go ahead and plug our y value into here, and we know that b equals y, so we know that b has to equal to 9 minus x squared. So if we plug that in, volume integral between -3 to 3 of square root of 3 over 4, and we know what our b is, which is 9 minus x squared squared with respect to dx. The only variable we have in there now is our x. So we just plug this into the calculator, and our volume comes out to be 112.24. So that's how you can go ahead and find the volume of these two different problems with these two different shapes. The first one was a square, and the second one was an equilateral triangle. Okay, let's do another problem. So what we're going to do about now, what we're going to talk about now is we're going to go ahead and look at, we'll just leave that for another video. It's going to be the area using when it's rotating an axis and using the cross sections, which is going to be called the shell method or the dish or washer method. I'll see that on the next video.